Okay, hello everyone. I'm Chanhua Chen. I'm the Senior Director of Architecture from ND's Technology. And today I'm going to briefly talk to you about the P extension test group status. Okay, the RISC-V P extension, the charter of this test group is that we want to define and rectify packed SIMD DSP extension instructions operating on general purpose registers and for embedded RISC-V processors. And then we also want to define compiler intrinsic functions and that can be directly used in high-level programming languages like in C. So for developers to easily use the P extension instructions. And I'm the chair, and the co-chair is Eric Fleming from Greenwaves Technology. And the proposal is that it's based on the ND-Star V3 DSP ISA we have developed before switching to RISC-V instruction set. And we want to use general purpose registers for the SIMD instructions. And it supports saturation and rounding, and it supports fixed point and integer data types. And for SIMD instructions, it supports 8-bit, 16-bit, and 32-bit element sizes. And there are also some partial and non-SIMD instructions that operating on 8-bit, 16-bit, 32-bit, and 64-bit data types. And for RV32, it has 64-bit sign and unsigned addition and subtraction instructions. And it also includes 64-bit addition with 16-bit and 32-bit multiplication reduction instructions. And why use GP instead of separate registers? Because we think that GPR-based SIMD instructions is a more efficient, low-power DSP solution for embedded applications. And especially for audio, speech, some IoT sensor data applications, and also recently for some lightweight neural network applications. And we think that it addresses the need for high-performance generic code processing as well as digital signal processing. And for SIMD operations, it has 16-bit element, and for RV32, it can do 2 parallel operations. And for RV64, it can do 4 parallel operations. And it supports various operations. And for 8-bit operations, it can actually do 8 parallel operations. And in RV32 and RV64, it do 8 parallel 8-bit operations, and also support various operations. And these two 8-bit and 16-bit, the operation they support doesn't have to be the same. Okay, it also includes, there are some partial SIMD operations that can do 2 16-bit multiplications and then accumulate it to a 2Y 32-bit result and do Q31 saturation. And it covers 6 times of baseline operations. And for RV64, and we duplicate that to make it 2 similar operations, and it covers 12 times baseline operations. It also includes 2 16-bit operations and accumulated to 4Y 64-bit result in RV32, and it has a 2.6 times performance of baseline instructions in Q15 dot product functions. And in RV64, and we do 4 16-bit multiplications and accumulate to 64-bit result. And it has a 3.6 times performance over baseline in Q15 dot product functions. And the extension also includes an 8-bit multiplication. It has to do 4 8-bit multiplication and accumulate also to 4Y 32-bit result. And it also a pretty good performance improvement. In RISC-64, and then we duplicate the operations to make it do 2 of this kind of operations in parallel. And it achieved approximately close to 8 times of performance improvement. And about 64 data types in RB32, and we propose to use pairs of GPRs to support the 64-bit data types. And then in RB64, it's already a natural data type, so you don't have to do anything special. And why we do that? Because we think if we support this 64-bit data types, then the compiler can automatically generate the DSP instructions for this 64-bit data type it will actually use frequently. And the 64-bit operand in the instruction actually is an interface specification. And the implementation can still implement 2 read, 1 write register file, and then use multiple reads and cycles to rewrite the register file to support the 64-bit data types. And you still get a performance improvement over the baseline operations. Okay, and we have tried the P extension instruction on several different benchmarks. This is a DSP library, and it has more than 200 DSP functions, and it covers in 8 categories. And we can see that in RB32, it has an average speed up 1.82, and for RB64, it has an average speed up 2.5. And the maximum speed up is much larger, but it depends on the functions. And we also try Helix MP3 decoder. At this time, we want to try the power of compiler without hand optimization, and just only use compiler optimizations. And then for RB32, it has a 1.95 speed up, and RB64 1.29 speed up. Why RB64 is smaller? Because in Helix MP3 decoder, you use 64 data types. So those 64-bit operations are already naturally covered by RB64. And we try several voice codecs, the P versus the baseline, and we get, depends on the codec, we get some speed up from 1 point something to 3 point, close to 4. Okay, we also try some neural network benchmarks, and the CFA10 is the image classification, and the PNet is the face detection. And we also get a very good speed up over the baseline instruction set. Okay, in summary, the current progress of the P extension test group, we have created the instruction proposal spreadsheet for test group members to review and to give feedback. And also we benchmark the DSP library functions for the usefulness, or several benchmarks on the usefulness of these instructions. And in all these benchmarks, around 100 DSP P extension instruction has been used in these benchmarks. And we also released the detailed instruction operation specification, and including the intrinsic functions in there. And we also, last month, we released a toolchain and simulator binaries for test groups to evaluate the use of these instructions. And anyone interested can use the toolchain to try out different applications they are interested. Okay, this is my status update. Thank you.
We've got time for one question, yes.
Just very short, the speed ups are computed assuming single cycle execution?
No, not single cycle execution.
So what latency do you assume?
Typical, we use a 5-stage in-order pipeline, typical latency for evaluation. So for example, Mac operation, it takes, we use pipeline, 2 cycles multiplication. And multiply add, I forget, sometimes we use pipeline and it takes 3 cycles. Yeah, it's not single cycle.
Okay, thank you, Chuanhua.